Daniel will start. I'm happy to introduce him today to be his chair. He's my office mate since starting of this year, doing a PhD in Vienna, and he will tell us about joint work, I think, also with Berlin.
Yes, Professor Rupert Klein.
So you have the stage, the pointer is here.
All right, so normally I prefer talking without the microphone. I think as we're right now, it should not be a problem. Okay, so the title of the talk is a new atmospheric boundary layer in a quasi-geostrophic framework, including moisture. So this is a new development in the field of geophysical fluid dynamics, and I think a very interesting one. And so since this builds heavily on traditional concepts from theoretical meteorology, like quasi-geostrophic theory and also the Ekman boundary layer near the surface of the Earth, I will devote about the first half of the talk to really properly motivating and introducing those concepts. And then we'll look at some of the new stuff. All right, so yeah, as I said, classical results is what the first part of the talk is devoted to. So we'll start just with the governing equations, which are the governing equations for flows of dry air, of course. So I mentioned moisture in the title. This will play a part, but not for now. Classical theory is all about dry air. So what do those equations look like? The momentum equations of Navier-Stokes or Euler type in a rotating frame. So the very first term is just an effective time derivative. Then we have the Coriolis force.
You also have a laser.
Where is it? Whether activated? Okay, right, very good. So that's the Coriolis force. These are the pressure forces. This is the acceleration of gravity, which of course occurs only in the vertical momentum equation. And F stands for frictional forces, which we will ignore for the most part. And we will specify them at a later point when we investigate the boundary layer. All right, then, and yeah, I want to point to the fact that the real distinguishing feature of geophysical flows is the presence of the Coriolis force, of course, and the effects of rotation that stem from it. Right, then conservation of mass is, I would say, as we're all used to it. And then we have an evolution equation, and instead of the temperature, we utilize the potential temperature theta, which is defined like this. RD is the gas constant for dry air, and CPD, the heat capacity of dry air at constant pressure. So those are just some physical constants. At least we can allow ourselves to take them constant for now. Let's make things unnecessarily complicated. And so the physical meaning of potential temperature is that if you adiabatically compress a parcel of air to the sea level pressure, then that's the temperature it would attain. Right, and a very nice property and why we use potential temperature is that under certain conditions it's a conserved quantity, right? So that's why we write the equation like this. So this is the time derivative along paths of fluid elements, and this is a source term that we won't specify for now. It stands for just about anything from internal dissipation to heat conduction and so on. And of course, to close the system, we need another thermodynamic relationship, which in this case would be given by the ideal gas law, which I didn't bother to write down. All right, then let's talk, before we actually start systematically investigating the whole thing, let's talk about the geostrophic approximation. So we have just the horizontal flow components, flow velocity components, and then this is the first part where we actually do asymptotics, but for now I'll just do it in a somewhat heuristic way. So if we can neglect friction, which we almost always can, and if this number is small, right, then something happens. And this Rossby number is actually the most important parameter in the whole theory of geophysical fluid dynamics, because what does it express? It's the ratio of a reference velocity to this term. And this gives us the relative speed of movements incurred by the rotation of our planet. So, if the Rossby number is small, then that means that the forces of rotation play an important role in the dynamics. And since we're investigating large-scale flow, that will be the case in all that is to come. And then a leading order balance emerges, which we will later derive properly, and it's called the geostrophic approximation. So we have U multiplied by the Coriolis parameter at the reference latitude. We have a background density, which is purely vertical. And here we have this product with the horizontal pressure gradient. So this statement here really means that geostrophic flow is perpendicular to the pressure gradient. And again, this is a characteristic feature of large-scale geophysical flows, because under normal circumstances, meaning there is no rotation, one would expect the flow to actually follow the pressure gradient. So, and here, just the rotation that affects each individual fluid element makes it behave like a spinning top. So it always veers off in the opposite direction. Okay, now the validity of the geostrophic approximation is for the most part limited to the mid-latitudes. Near the equator, we need a completely different approach. But now we're interested in mid-latitudes, and there we can build a closed system that is based on this geostrophic approximation. All right, so now let's get into the scaling. The need for a distinguished limit. So what's that? If we want to systematically investigate reduced models where some small parameter epsilon goes to 0, then we need to scale our equations first. So we choose appropriate scales for length, time, velocity, and so on. And the crucial underlying assumption here is, which is of course not very natural for the mathematician, that every quantity is characterized by one single scale, right? So this is something that holds true for large-scale flows, where turbulence is parameterized and does not play a role directly in the equations. But of course, in general, this would be a very sweeping, grand statement, right? So in doing that, we do not only get the Rossby number, but other fluid dynamical numbers, and the most important ones here would be the Mach number, which gives us the ratio of reference velocity to the speed of sound, and the Froude number, which gives us the ratio of reference velocity to this, which is basically the barotropic gravity wave speed. And one could imagine this would, for example, be long waves in shallow water. Right, and proper scaling, yeah, that's what I already mentioned, right? So this stays true as long as we do not enter a boundary layer. So that's the heuristic principle that all of the boundary layer theory is based on. Once we are in a boundary layer, the relevant scale is shortened, which means the gradient with respect to the variable will increase in magnitude, and that will alter the leading order balance between the individual terms in our equations. Right, so yeah, in many instances, and in our specific case, those numbers are all small. Oops. are all small. And a distinguished limit is one that ties them together by expressing all of them in powers of one small parameter, epsilon. Right? So in order to obtain a unique limit, of course, we need to do that, otherwise limits would be path dependent. And that can actually be seen by considering a very simple example. So if we just take the linear oscillator with small mass and small damping, then you will see that if you let both of those depend on each other, depending on the relative magnitudes, we obtain, I think, 3 different limit scenarios. Right? So that is a very useful motivator just to see in an instance where you can actually compute the solution, what is happening. Right? But of course, now this choice isn't arbitrary at all. Because first of all, there are physical constraints, right? So only balances between certain terms in, let's say, the momentum equations make sense. And also, there's the mathematical concept of a significant limit, right? So if we lose too many terms with our choice, then our limit might be contained in another limit, meaning that we just lose information and do not gain any compared to the other one. And now, if we, so yeah, now I didn't actually mention that this is the limit that we will be using. So the Rossby number is of the order epsilon, and the squares of both the Mach and Fruit number are epsilon to the third. Actually, in many instances, those two are equal. And this is a limit that is due to Rupert Klein. He introduced it actually a few years earlier, but in this review article in 2010, he summarized all the characteristic features and presented it in the form that we use today. Right? And again, this is just one possible choice, right? There could be many other distinguished limits that are equally valid for certain situations, but the main advantage of this is that if we just rescale individual space and time variables, if need be, then we can obtain a great number of classical, well-known for the usefulness approximations, just by employing one scaling, one basic scaling, and one distinguished limit. So to all of those who work in fluid dynamics, it is clear why this is very useful, because traditionally the notation isn't unified. It's sometimes very hard to see how 2 different derivations relate to each other, because the scalings are a complete mess. So this is quite important for just obtaining some clarity, right? And now, again, I will mention it again, the most prominent of those approximations, and probably the classically most successful one, is quasi-geostrophic theory, which describes very well many characteristic features of large-scale flows in the mid-latitudes. All right, so again, we can neglect friction. And we also specify that the aspect ratio is small. This is the ratio of the vertical to the horizontal length scale, which is quite natural if you just think of the shape of our planet and the atmosphere. So the height of the atmosphere is very small compared to the radius or circumference of the Earth. So in this case, we estimate it to be the order epsilon squared. And then the non-dimensionalized and rescale equations read like this. So yeah, basically I don't think I need to reiterate. Here we separated out the momentum equations in the horizontal and the vertical part because of the above, right? And here we can already see these factors are supposed to give a balance between the pressure forces and the Coriolis force. Here we will obtain something that is called hydrostatic balance, which I will introduce in a moment. And here we have just conservation of mass and the evolution of potential temperature. And also you will notice that the Earth rotation vector has been replaced by something a little simpler. And this is done in the beta plane approximation. So in the beta plane approximation, we replace a coordinate system which is, well, to first order spherical, because it isn't precisely spherical, by a locally Cartesian one around the reference latitude. So it means we linearize the Coriolis term, and we can now proceed in Cartesian coordinates, which is of course a great advantage, because in spherical coordinates the calculations will be a lot messier most of the time. All right, so I think that's it for the preliminaries. Now we can actually start deriving something. All right, so asymptotic expansions, I think everyone is more or less familiar with. So all those quantities, in order for this to make sense, F0, F1, F2, and so on have to be O of 1, so that the relative magnitudes are only determined by the prefactors. Okay, and the thermodynamic state variables, pressure, density, and temperature, they have purely vertical profiles at leading order and up to the first order perturbation, right? So now, for the physicist, at least, it is clear that the leading order terms for large-scale flows should have purely vertical profiles, because we can separate those state variables into a background state that is derived from an atmosphere at rest, and then perturbations from that, right? But we can actually use the formal asymptotic framework to prove that if this is the case, then also the first order perturbations have to be purely vertical, right? So this is something very nice. We can actually do mathematics and not just model physical understanding. And then, so if we just insert those expansions and collect terms of the same order in epsilon, we recover the geostrophic balance. So we'll see here we have U0 and P2. So P2 is the first pressure term in the pressure expansion, which actually has a horizontal gradient. That's why we obtain this balance. From vertical momentum, we get what is called hydrostatic balance. So the leading order pressure is determined, its vertical derivative, by minus the product of acceleration of gravity and the leading order density. Conservation of mass yields that actually, even though we already rescaled, the vertical velocity is even smaller. So it vanishes at leading order, and next order we obtain this, which is known as an inelastic constraint. All right, now so we also have an evolution equation for the potential temperature, which is, I think, there's nothing surprising in there. We've separated out the vertical background profile. And now Q theta is supposed to indicate the strength of diabatic heating, right? And if you consider the horizontal momentum balance at the next order, now we get something very interesting. So, of course, I skipped all the calculations. We're only interested in the result. And that is an advection equation for what is called the geostrophic potential vorticity, right? So it's defined like this. This is the vertical curve. This is the contribution of the planetary vorticity, the Coriolis parameter. And here we have this term, which involves mostly the potential temperature. And now, this quantity, horizontally advected, then is determined in its evolution by this term, which is of course zero if there is no diabatic heating. So we obtain the conclusion that without any diabatic effects, this is a conserved quantity along Lagrangian paths, right? As it should be, of course. And then it's also quite easy to see, since in this instance, at leading order, the horizontal divergence vanishes. We obtain the pressure as a stream function for the vertical vorticity accordingly. And if we then determine the pressure with a known background state, this potential vorticity completely determines the system's dynamical evolution. Right, so this is a very nice mathematical property of the system. And now, of course, I could talk a lot about the potential vorticity, but I think that would be getting too deep into the meteorology of the problem. So, yeah, we'll just skip it for now. And continue to the next important concept, which is turbulent friction in the boundary layer. And that leads us to the Ekman layer, which is just traditionally known as the boundary layer near the surface. So the surface might, of course, be the ocean as well, but that is much more complicated to treat because it's a moving surface. And so we will restrict our attention to solid ground. And in that case, well, again, we cannot neglect friction anymore, just for purely mathematical reasons, because otherwise the order of our equations would be too low to fulfill all the boundary conditions that we impose on our system. Right, now the big problem here is that there is no proper mathematical theory of turbulence, at least not yet. And so the effect of turbulent friction on a small scale on a large scale flow is very difficult to gauge. And the simplest model, which certainly isn't completely accurate, but it's the best that we got, is provided if we just parameterize the Reynolds stresses in the simplest manner, which then leads to an expression like this. So this term, with the dynamic viscosity, is actually the one arising from the molecular viscosity, which we know from the traditional incompressible Navier-Stokes equations. And these terms here, if we just identify AH and AV, actually have a similar structure, right? So if those two were equal, which they are not in practice, then we just gain a molecular viscosity which is artificially enlarged, right? So this can maybe motivate a little why we choose terms of this shape. All right, and AH and AV are called horizontal and vertical turbulent friction coefficients, respectively. These will be assumed to be constant in the following, which is, of course, even less accurate than the preceding. But again, it's the only case where we can actually obtain a satisfactory mathematical picture of the situation. Okay, and yeah, an analysis of relative orders of magnitude, which we'll skip here, it's not terribly interesting, yields that the dominant contribution comes from this term with the vertical turbulent friction coefficient. And this is mostly due to the fact that, especially in the boundary layer, the thickness, which is the order of the vertical scale, is much, much, much smaller than the horizontal scale. Right, so that's where this term then dominates. And then here we also have to introduce a new dimensionless number, which is the Ekman number, and it just naturally arises from a non-dimensionalization of the system. And in order to actually obtain a leading order contribution of friction, we will scale it like this. So it's of the order epsilon squared. And then, of course, in boundary layer theory, which I also already mentioned, we have to consider the thickness of the boundary layer, which leads to a rescaling of the vertical coordinate by some power of epsilon. And in this case, the correct choice is simply zeta z over epsilon. And yeah, what I already said, it elevates the friction term to leading order, and then we get from horizontal momentum this, which of course now destroys geostrophic balance, which is kind of what we expected. And now I won't write down explicitly all of the resulting equations. So basically we just have added terms in the horizontal and vertical momentum balances. And then the real task, the real challenge is to match this boundary layer flow to the QG flow. Right? So how do we do this? In a general form, this can be very complicated and a real mathematical task, but the simplest form of the matching principle is we just express the boundary layer expansion in terms of the outer variable, so which would be z in this case, then we re-expand and we will obtain the outer expansion again. Or we can do it the other way around. So we take the outer expansion, which is the QG flow, we substitute z by the rescale variable, we re-expand, and the limit will then obtain the flow in the Ekman layer. Right, so the primary result that we get from this matching is that W tilde 1, which is the lowest contribution to vertical velocity in the Ekman layer, at zeta infinity is given by this, which is 1/2 the vertical vorticity in the QG flow. Right? And then a very simple application of the matching principle leads that this actually gives the lower boundary condition for QG flow. So what does that mean? This mechanism is known as Ekman pumping. And so what happens is the following. One relation that I didn't write down is that, of course, the boundary condition for the pressure in the QG flow fixes the leading order pressure in the Ekman layer, right? So it's this pressure that then produces motion, and in particular also this vertical motion, which gives us again a boundary condition for the vertical velocity in the QG layer, right? And so we have a feedback loop. This again influences the pressure, which is transported down to the Ekman layer, and then the pumping up of vertical velocity brings us back to the start. And I mention this now because later on I will get to know an advanced version of this. We'll get to that in a few minutes. All right, so main sources for that, of course, the classical book by Belowski, which contains everything that I just mentioned and a whole lot more. And as far as the distinguished limit is concerned, that's the article by Rupert Klein from 11 years ago, Scale Dependent Models for Atmospheric Flows. Okay, so okay, very good. So the diabatic layer. Now this is the first actual new development that I wanted to talk about, and it's also based on work done by Professor Klein, who I worked with last month in Berlin a little bit. So what are limitations of quasi-geostrophic theory? First of all, if we recall the expansion of potential temperature, we have a constant background state and then a first order perturbation that is purely vertical. Right, so, and now if we just substitute reasonable physical estimates for those values. Let's say our reference temperature is 300 Kelvin, and epsilon is now supposed to be around of the order 1/10. So, why is that? Because in many instances, 1/10 is just what we consider the distance between two separate scales, right? So, of course, mathematically, we want epsilon to be as small as we like, but as all our derivations are formal, this is actually not an issue, right? So, this is done all the time in geophysical fluid dynamics, and it actually leads to very reasonable approximations. So, anyway, if you now take the expansion of potential temperature in quasi-geostrophic theory, this implies there are deviations of the order about 3 Kelvin from the background certification, right? Because that's the term O of epsilon squared. And the diabatic source terms, by the evolution of potential temperature, then have the same strength. So this is actually not too bad when you just consider long time average data. But if you look at, for example, cloud-topped boundary layers on heat fluxes near the ground, latent heat release by cloud formation, then we can observe heating rates that greatly exceed that value, right? And furthermore, if we take this estimate and then try to estimate precipitation rates based on that, then those are far too low. So we get practically no rain. And even though right now we are not considering a moist model, one of the ultimate goals is to incorporate moisture into that, which I will also talk about at the end. And then, we also should keep in mind that most moisture in the mid-latitudes is stored in the bottom few kilometers of the troposphere. So this is what we want to take a look at. Not the Ekman layer, but an area just 2 to 3 kilometers above that. Okay, so what's the structure of the diabatic layer going to be? Motivated by those observations and estimates that I just mentioned, we want to introduce an additional boundary, or maybe more appropriately called a transition layer, that covers that area, the lowest few kilometers. And for that, a natural choice for a layer variable is just rescaling set by the square root of epsilon. Right, so with the physical estimate of epsilon that I mentioned before, this gives us about 3 kilometers, a little more than that. So it's an excellent agreement with what we physically aim at. And this choice, now, why is this relevant? Why is this important? And now comes the real juicy part. So if we just tailor expand the QG potential temperature, so this should be θ1, the background certification, in terms of the rescale variable, right? So we're kind of emulating the matching principle right now to try to get the right idea. Then we get the result. This is 1. This is also a constant term. And here we have epsilon to the 3/2 times eta times that derivative. And now the idea is, in a boundary layer, we have some qualitative change of the motion, right? Otherwise we wouldn't need it. We could just proceed with one expansion and would be done with it. So in this case, the idea is that in the diabatic layer, we replace the latter term by a function that varies in space and time in all the coordinates, and this is now the expansion ansatz, right? So all the above was just motivation and what we want to achieve, and now this is what we just postulate that the expansion will be, right? So here we just have a constant term, but here, so the leading order variability is not just of lower order in epsilon, 3/2 instead of 2, but it also immediately ties together all the deviations from a constant background state. Right, as far as the other variables are concerned, there's nothing too special about the expansion ansatz. And of course we have, since this is a boundary layer for the QG flow, constant pressure and density at leading order. Right, so the equations otherwise are exactly the same, except for the shifted orders of individual terms that have derivatives by the vertical coordinate, but I don't think we need to look at them again explicitly. Okay, so the calculations that we do, they are greatly simplified if we introduce the Ekman pressure, which is just P to the power of gamma, which is the ratio of gas constant for dry air and heat capacity for dry air to constant pressure, which we could observe before already. And then, so the results are, first of all, we keep geostrophic balance. That's very important. We lose geostrophic balance in the Ekman layer, but we keep it in the intermediary transitional layer, the diabatic layer. We also have hydrostatic balance, which for deviations from the background stratification actually has this form. So the vertical derivative of the pressure is given by the potential temperature, right? And again, transport equation for the potential temperature, which is nothing to write home about per se. Right, and now we want, of course, we also need to match that to the Ekman layer, but that's quite straightforward. So the really interesting part is matching to the QG flow. And here, higher order considerations, yeah, again, we get that up to O of epsilon, the vertical velocity is independent of eta, which means that it is just lifted through the diabatic layer, unchanged, right? And since geostrophic balance is maintained in the diabatic layer, we immediately know that if we can successfully match the pressures, the extra pressures, then we also get the matching for the horizontal velocities, because those are immediately determined by the former. So, yeah, for the vertical velocity, since it is preserved through the layer, we get bottom boundary condition again, right? And yeah, the potential temperature, so yeah, in order for our postulated scaling to be valid, this condition needs to be fulfilled, and looking at the evolution equation of potential temperature, this will be the case if just the source term goes to zero quickly enough as eta goes to infinity, which is a very natural assumption since when we leave the diabatic layer, then diabatic source terms are supposed to become accordingly weak. Okay, and so the matching of the Ekman pressure results in this expression. So the difference between the two layer pressures is given by this. So here we have the leading order deviation of potential temperature. And we can see that this is in general going to be substantial, right? And that's important because I mentioned before, so in Ekman boundary layer theory, we have pressure that is imposed on the Ekman layer by the QG flow. So in this case, the pressure changes maybe dramatically throughout the diabatic layer and then is impressed upon the Ekman layer by the former, right, by the diabatic layer, and not by the QG flow. So this, together with different expansion of potential temperature, gives us a much more differentiated, varied picture of the Ekman pumping. And in fact, all of this hasn't even been published yet, so it's only available as a preprint right now, but you can go read the paper on arXiv if you want to, dynamics of a diabatic layer in the quasi-geostrophic framework. And now, just very briefly, I want to talk about the next step, which would be to incorporate moisture. So, moist QG models, there are a few already, but they're very limited in the scope, and yeah, there are very few attempts to extend classical QG theory systematically to include moisture with phase changes and precipitation, right? So, one of the more recent attempts was in 2017 by Leslie Smith and Sam Stackman, who derived the QG model with moisture using the so-called FAIR equations as a starting point. So FAIR stands for fast autoconversion and rain evaporation, which vastly simplifies the dynamical picture as far as the evolution of the moisture quantities is concerned, because in this case we can actually restrict ourselves to just one equation for one moisture quantity, which would normally be just the ratio of water vapor, right? Mixing ratio of water vapor, that's what it's called. So, and still, apparently, so this has actually been used as a cloud resolving model and seems to have had some success, which motivated Smith and Stackman to use it, right? And initially they used the simplest version where the density is constant, and we have vertical background profiles for all quantities that are thermodynamical, including moisture, right? And that is kind of controversial, as we will see. So, vertical background profiles are indicated by tilde, and those without are actually just deviations from the former. So if you see something like a P, that's not the complete pressure, it's just the higher order deviations. Now, and that's what the system looks like, right? So it's kind of different because, as I just said, it's actually expressed primarily in terms of the higher order deviations from a vertical background state. So here we actually have an incompressibility condition, and this is the evolution equation for the moisture quantities I just mentioned. Theta E is given by this, and it's known as the equivalent potential temperature. So I explained what the potential temperature is supposed to represent. The equivalent potential temperature is kind of the same for moist air. So if we compress to the sea pressure some parcel of moist air, and we drain all the moisture from it, then the temperature that would be attained is supposed to be the equivalent potential temperature, and it's also conserved under certain conditions, which is why we have this form of the equation. And of course, here for precipitation, we have to consider the terminal rainfall velocity, which here is just taken to be constant, and actually its scaling is also kind of controversial. All right, so pros and cons of this model. It's straightforward. Its scaling is consistent with classical approaches to quasi-geostrophic theory, and also something very nice that Smith and Stackman derive in the paper is that, analogous to the QG potential verticity fully determining the QG flow, here we do not, of course, one such equation is not enough, but we can do it with two variables. So one appropriate potential vorticity, and the other is a suitable combination of moisture terms and the process is called potential vorticity inversion. Also, they derived an energy principle for the model equations, which is, of course, very nice to bolster the physical accuracy of the model. But, especially as far as this is concerned, some assumptions are dubious, and I talked at length to Professor Klein about that. So, first of all, that the moisture components, so the mixing ratios of water vapor and rain, are separated into a background certification and almost done. And deviations from that is something that is not in general accurate, right? And then we have the scaling of the terminal rainfall velocity, which here is taken to be very, very small. So it's about of the order of 1/10 meter per second, and in practice, most of those velocities are actually more than 1 meter per second, right? So those are problems because the resulting equations that they obtain are very nice, but they rely on assumptions that are not actually accurate in reality, right? And the underlying model might be too restrictive to begin with, so challenge 1, and that is what I started looking into it. We looked for an alternative model that is a little more elaborate than the FAIR model, and this should happen in the framework established by Rupert Klein. Challenge number 2, once we have found a good model, we incorporate the diabatic layer into it. Right, so yeah, just very briefly flash a possible alternative that I sketched during my time in Berlin. So we now consider compressible flow. Right, you can see, of course, yeah, we use the same scaling as before. We keep the equivalent potential temperature as a for the inner energy, and now we have 2 evolution equations instead of 1 for the moisture quantities. All right, so now that's the kind of final statement. So the first observations that are made, if we remove the vertical background profile for the moisture components, then the equations that we obtain are a lot different. The evolution equation for equivalent potential temperature might have to be replaced by a more elaborate one as well. And the incorporation of the diabatic layer doesn't seem to cause any difficulty with the matching, but it does not seem to give us much insight as expected, so we might need a different ansatz for the moisture variables. And maybe the terminal rainfall velocity should be parameterized as a non-constant quantity. And all of that is in the future. Yeah, and thank you for your time and attention.
Thank you very much.
So I have one simple question. Maybe I missed it in the very beginning, but why is there is term geostrophic, and then what we do quasi there in this model?
What is the term?
Geostrophic.
Geostrophic, yes.
Well, like where it comes from?
Oh, where it comes from? Well, that's actually a very good question. So, geostrophy, I never looked into the etymology of the word.
Then the other question.
Right.
So there is a classical theory of geostrophic theory,
Yeah.
and then there's a quasi one. So what is the quasi in there?
Okay, so yeah, geostrophic just refers to one approximation, right? This is not a complete model, it's not a closed model, because we don't know anything about the pressure heat. And quasi-geostrophic theory is just the extension of the geostrophic approximation to a consistent approximative model. So, yeah.
But yeah, it should be still not full, right?
No, of course, it's an approximation. But of course, you know, especially on those large scales, we consistently try to establish model hierarchies because we want to compute something, right, in the end. And that's impossible if we use the full compressible flow equations. So that's why we try type, right?
Most typical fluid simulation on Earth. And so we usually consider a no-slip condition in the boundary. So I was wondering if the boundary layer analysis gives us a different interpretation for what's happening there. Like, should we modify the condition? Is it accurate?
No, to get it right, this is just a general question about what the boundary layer tells us.
Yes, it gives information about the boundary conditions that we will consider them, let's say,
in a way, yes, because if we look at a nonlinear problem, then of course the boundary values dramatically influence also the form of the boundary layer. So yeah, indirectly. But in the end, it's just a necessity because, of course, if we just had full equations and we could work with them, we wouldn't need any boundary layers. But the point is that so many times in fluid dynamics especially, we need to use an approximative regime which leaves out some information. And now that information makes it impossible to fulfill all the boundary conditions at the same time. And that's why we need to do all that boundary layer stuff.
Okay.
Right.
Any other questions? I have one, but since we are late, I will ask you later.
Yeah, sure.
And thanks again for the speaker.